All right. Good morning, learners.
Morning, ma'am.
How are you?
We are fine and you?
I'm good, learners. Today we are starting an exciting topic called Fundamentals of Electronics. And electronics is all about how electricity flows through small parts called important components. We learn about today, they are going to learn about the resistors, capacitors, and power sources in a circuit. So what you need to understand is a resistor slows down the electricity, and a capacitor, it stores and releases energy, and the power source, which is a battery, it's used to give the circuit energy to work. So now I'm going to draw the circuit for you so that you can also give me some answers about today's. We know that these things, they work mostly in as part of the today's world, the electronics. So they make the electronic devices like cell phones, TVs, and toys and other functions. So today we are going to speak about our topic. It will be about the RL, RC, and RLC. But what I'm going to do is I'm going to concentrate basically on the RLC circuit, but in a series connection. So on this one, because it's the combination, once I said I've explained the RL circuit and the RC circuit, it means when I explain the RLC circuit, it's the combination of everything. So I'm going to draw a circuit for you to give you the scenario of how does it look like. Are we together, guys?
Yes.
Okay. So the circuit will be looking like this. A series RLC circuit. Series let's say RLC, which means R stands for the resistor, and L stands for the inductor, and the C stands for the capacitor. If I explained during my explanation what is the aim of the resistor in the circuit, which is to limit the current, and then this one is to store the current. So meaning that I will start with a symbol of a resistor in a circuit. You can use this one because there's also the other symbol that you can use. You can draw it like this, which is also a symbol of a resistor. But I'll prefer this one for now. And then this is our inductor, and this one is our capacitor. So in a circuit, a closed circuit, we do have a source. A source, which means it's our battery, our supply, isn't it?
Yes.
Which is in voltage. And then we still have the current. So the current that flows from positive to negative, which is our current here. Current that goes into a series circuit. And then in between, we still have the voltage drop across the resistor, and the voltage drop across the inductor, and also the voltage drop across the capacitor. But bear in mind, guys, that in a series circuit, when we talk about the Kirchhoff's, we've got Kirchhoff's current law and Kirchhoff's voltage law. So the Kirchhoff's current law, it says that the current in a series circuit, it's always the same. As long as it's in series, the current is the same. If the current here is 3 amperes, it means our current on the resistor, it will be 3 amperes. And if our current on the inductor, it will be 3 amperes. And our current on the capacitor will also be 3 amperes. That's how we obtain voltage current law. The current that flows in this. So what we are going to use here, because I'm going to teach you about the calculations, how to calculate the impedance of the circuit and the phase angle of the circuit using the RLC circuit at this level, which is for level 4 basically. Are we together, guys?
Yes.
So now I will also be presenting the formulas here. So you guys will have to note down the formulas and write them down so that when I'm going to give you an exercise, you need not to refer. I'll prefer you guys not to refer so that you get used to the examples that I'm going to give. So now, I will ask some questions concerning the RLC, how it works and how you are expected to understand it. So if I may ask, can you name a device at home? Because we use devices in the components. Electronic components is our devices. So can you name a device at home that may use a coil? A coil which is in the form of an inductor. Inductor is also a coil. What can you say?
Speaker.
Yes, Malema?
Speaker.
A speaker. It does have a coil. Are we together, guys?
Yes.
All right. Then, the other question is, why do you think a resistor is used with a capacitor and a charger? A capacitor and a charger in a real life example. Why do you think a resistor is used with a capacitor and a charger in a real life example? So what, yes, what's it? Ntsuniki?
To limit the current.
Yes, the resistor is used to control. Listen, the yes is correct. The resistor, yes, in that, because it's used with the capacitor, it controls the speed of the electricity. Are we together, guys?
Yes.
And then secondly, the capacitor, it stores electricity and then gives it slowly, and they work together to protect either the phone or the television that you are using at home, because we are talking about the devices. Are we together, guys?
Yes.
Yes. So now, let's get to the work. So, as I've explained that the resistor limits and slows down the current or electricity, and the capacitor, it stores the amount of energy. And then the examples found in the components, the appliances, when we use the resistor, it will be TVs and radios, and also the capacitor, we can say the phone chargers and flash cameras, because they store and release small amount of energy they use to charge, isn't it?
Yes.
Okay, what about the battery source? It gives power to the circuit, because if we've got a battery here, remember this is negative, the battery is used to give the power to the circuit. Are we clear?
Yes.
It's like when we use a remote at home for a TV. So it also, it has got batteries, isn't it? There's no way that you can operate that remote without batteries. So that's why we're saying the battery is used to do what? It gives energy. Okay, now, an RLC circuit in a simple way in level 4, what you need to learn now, this is very, very important. We are getting to the most important part of the work. In level 4, normally I use what we call Ohm's law. Ohm's law says the current that flows in a circuit. This is the current. Can you see the current flows positive?
Yes.
The current that flows in a circuit, a closed circuit, is directly proportional to the voltage and inversely proportional to the resistor. Are we together, guys?
Yes.
So in a simple form, Ohm's law, I always use this so that students must understand. This one is in ohms, resistor, and this one it will be in volts, and this one will be in amperes. So basically this is Ohm's law. The current that flows in the circuit is directly proportional to the voltage and inversely, because now it's inversely proportional to the resistor of the circuit. Are we clear, guys? So now, here, I'll put a multiplication. And here, I'll put a what? A division. So what does it mean? It means if I have to calculate the current, total current of the circuit, if I'm given the voltage and the resistor. So which means I will close here, meaning that if I'm looking for current, I will say I is equals to V divided by R. This is how we put it. Can you see that?
Yes.
Then, if you are asked to calculate the voltage of the circuit, then you will say V, you are looking for V, will be equals to current multiplied by resistance. Then when we come to the resistance, what will be the formula? R will be equals to, and then give me the formula. Remember I closed here. What am I left with?
Divided by
V divided by I. That's how you calculate the resistance of the circuit. Then the answer here will be in amperes, and the answer here will be in volts, and the answer here will be in ohms. This is the symbol of ohms. Or if you don't know it, you just write ohms. And this one is volts. And this one will be amperes. Right, now this, normally we have learned this in level 2 and level 3, most in this subject of electrical principles. That's where we're dealing with a lot of calculations, whereby we were using these formulas. But now, this topic is also, it correlates again with the level 4 principles also. I think it's also in topic 1 of level 4. For those who have already attended level 4, they might have done this already. But I'm not saying we are not going to do it. We are still going to do it. Are we together, guys?
yes.
Yes. So now, so we go extra by saying with this, because in level 2 and level 3, we were only using this formula up to here. Then we take it further. Taking it further, you also need to calculate the inductive capacitor and the capacitive reactance. This is the inductive reactance, capacitive reactance, and the impedance of the circuit. All these, they are also calculated in ohms. It doesn't mean because it's XL, because now you will say, okay, L, which is the inductor, is in henries. And then C, it's in farads. But Z is also in ohms. Then we must bear in mind that there's also the frequency that is also applied here. Are we together, guys?
Yes.
Which is also in hertz. So I'm gonna just give a classical example and give you the values whereby we can just do few calculations based on these formulas. So once you get used to this and you are given a formula sheet, there's no way that if you are given a circuit in series RLC, you can be able to calculate everything by using only these formulas. Are we together, guys?
Yes.
So let's start with the first one. Let's say maybe we are given 20 volts, and here we are given how many? 3 ohms, and then here we are given 1 millihenry, and here will be, let's say 1 millihenry, and here we are given 0.1 microfarads, 6 millihenry. So with our prefixes, we know that a micro is 10 to the power power minus 6. And milli is 10 to the power minus 3. And if we're given a kilo, if it's 3 kilo ohms, it will be 10 to the power 3. So now, they say to you, calculate the impedance of the circuit. Impedance of the circuit. Now you start saying, okay, I don't know the formula to calculate impedance. So the impedance of the circuit is being calculated like this. Our impedance, which is our Z, we use the theorem of Pythagoras. You still remember in maths we use the theorem of Pythagoras, isn't it?
Yes.
Okay, so it's going to be r squared plus into xl. You know why I'm doing this? Can you see this is not a minus or it's not even a plus, isn't it?
Yes.
So what does it mean here? It means that either one of these, the one that is greater than the other one, will subtract the other one. Meaning that if XL is greater than XC, here we put XL minus XC. If XC is greater than XL, here you put XC minus XL. That's how this thing works. Are we clear, guys?
Yes.
So now, we are not given, let's check. It's 20 volts and 50 hertz. The current is not given at all. The total current, we don't have the total current at all. Which means now, we should also calculate to get our total current. Since we've got the formula, we have IVR. But now, we cannot use this one because this one already, which is a circuit, RLC circuit, we cannot calculate, use the R, we must use Z. Are we together, guys?
Yes.
Meaning that now the impedance of the circuit, we start by calculating XL. So XL will be equals to 2 pi FL. That's the formula to calculate XL. Please note it down, that one. Don't forget it because we are still going to apply this. And then XC, the capacitive reactance, is equals to 1 divided by 2 pi FC. Then the next one is you get the value of the inductive reactance in ohms. And then from there you get the value of the capacitive reactance also in ohms. After this, then you take these values, you substitute them here. Are we together, guys?
Yes.
So now you take the resistor, you still use this one. Are we clear?
Yes.
Because here we've got the inductor, you would have calculated the inductive reactance. So if maybe, let's say maybe our inductance is it's gonna be 6 ohms and our capacitor maybe it's 4 ohms. Which one is bigger between XL and XC? This is our XL. This one will be our XC because it's already in ohms. Which one is bigger here?
XL.
XL is bigger. So meaning that on the formula, what are you going to do? You are going to say, when you use this formula, you are going to say our impedance is equals to the square root of R squared. Our R is how much? 3, isn't it? So it's going to be 3 squared plus our XL is equals to 6 minus 4 into brackets squared. So this is now 3 squared is how much?
9.
And then 6 minus 4 is 2. 2 squared is 4, isn't it?
Yes.
And 4 plus 9 is? This is 9.
13.
Is 13, isn't it? So which means we're going to have the square root of 13, which is our answer. The square root of 13 will be. Then you get the answer, but your answer will be in what? In ohms. Are we clear?
Yes, ma'am.
Now you've got the impedance of the circuit. You've calculated the impedance already. You know, here you get something like, sometimes they give 3 to 5 marks. So maybe you get 3 marks for here, you get 1 mark for this, 1 mark for this. You get that you are having 5 marks already, which is very much important. That's got a lot of marks. Are we together?
Yes.
Right. Secondly, let's move on this one again. We know how to calculate inductive reactance, which we have used 2 pi Fn. We know how to use capacitive reactance, which is 1 over 2 pi Fl, isn't it?
Yes.
Then we know how to calculate the what? The capacitance. Now, on the very same second, then they say to you, calculate the total current to IT. Because we have the impedance, which is our Z total, then we can be able to calculate the total current. But someone might come and say, yes, I know Ohm's law, so it means I must say it's I is equals to V over R. No, you are no longer going to use this. I'm closing it. Are we clear, guys?
Yes.
So what you need to do is you are going to use only the total of everything here, because on the circuit already you've got a capacitor and an inductor. If you use this, it means now you were only given current, voltage and resistor. There was no inductor, there was no capacitor. You can't use that. Are we together, guys? So I think it's understandable. Why are we going to use this? Because of these 2 components. You get it?
Yes, ma'am.
Perfect. Now, I'm going to say my I total, I've closed here. It's still the same. Look at this. It's gonna be V, give me. So it's gonna be V divided by V divided by V total over Z total. Because these 2 now and this one, they've given us a total impedance of the circuit. Are we together, guys?
Yes.
So now, which means now I am going to have 20 volts divided by whatever that I got there. If it's our impedance, maybe is what is the square root of 30? Sorry about that. Square root of 13. You can give me the answer if it has got to 3 decimal places. It's fine.
3,606.
3,606. Someone might say 3,61. Look at this.
Yeah.
Someone might say 3,61 is still correct. There's nothing wrong. Are we together, guys?
Yes.
Because it means you have converted this one to the nearest number. So now, if it's 3,606, I can say it's 3,61. 20 divided by 3,61 is how much?
5,54.
So our I total is equals to 5,54 amperes. Can we prove this? Can we prove this? Can we prove that if we add all these 3? Because in a series now, we can't prove it, because in a series circuit, I total is equals to I1 is equals to I2 is equals to I3, meaning I total is equals to IR is equals to IN is equals to IC. So it means that the current that is here is equals to this one is equals This one is equals to this one. Are we clear?
Yes, ma'am.
So, let's see. So if my IR is 5,4 amperes, this one is also 5,54 amperes. All of these are also the same. So now, they might come and say, calculate the voltage drops across each component. Which ones are our components? Resistor, inductor, and capacitor. But they need us to calculate the voltage drops. Because if they say, I total now, we've got all the current. The current through the resistor is the same, the current through the inductor is the same, current through this is the same. So let's calculate this one. We still go here. This one is a bit tricky. So now you want VR, you also want VL, you also want VC. Let's look at our diagram. So now I need V. But it's the first V is for VR, the second V is for VL, the third V is for the capacitor is the voltage across the capacitor, voltage across the inductor, voltage across the resistor. So VR, because V is equals to I multiplied by R, so it means here I will say is equals to IR. Remember, IR is also equals to I total, isn't it? So because I'm looking for I, it's equals to IR times R. Now I'm looking for this one. It will be IL times XL. Can you see that? Now the voltage across the capacitor, it will be IC multiplied by XC. So here I'm going to use the same value, here I'm going to use the same value, here I'm going to use the same values, but for resistor, I will take 3 across the across the inductor, I will use XC, and then across the capacitor, I will use XC. Yes. So now, this is how our formulas are going to look like. So even if you go to your textbooks, if you check in your textbooks, I will also take mine. You can also take yours, and then we verify the formulas. I will also take mine, and then we verify the formulas. If we go to our textbooks, I will tell you which page is it, so that we verify if I'm giving you the right formulas. All right. If you take your books and you open page 32, you open page 32, you'll find that the formulas are still the same. The formula for the impedance is the same. We have given an RLC circuit with a 10 ohms resistor, and then the inductor is 0.2 henries and the capacitor is 4 microfarads. So it's been calculated. You must calculate the impedance. They still use the same formula. And then the second one, they were saying you must calculate the total current, which is equals to I is equals to V over Z. Then from there, number 3 is the voltage drop across the resistor, and the voltage drop across the inductor, and the voltage drop across the capacitor. So all this is going to be in volts, everything here. Are we clear, guys?
Yeah.
In that book is the same. Now, Then you will be asked to calculate the phase angle. Phase angle, guys, this is not the last. Phase angle will be tan theta. The phase angle is this, but we studied by tan theta is equals to, what did we say? XL was bigger, isn't it? It's equals to XL minus XC divided by R. But we are not looking for tan theta. We are looking for theta. Is equals to the tan of minus 1 into XL minus XC divided by R. Then you get your answer, and then it will be in degrees. That's it. That's all. These are the formulas. So I think up to now you are now familiar with these formulas, and that will be all, guys. So we have discussed everything, the formulas to calculate all the RLC circuit, so you can be able to do that. Are we together, guys?
Yes.
Thank you so much.